Good day. My name is Tarek Fadi, and I am here to introduce you to our Waterwheel project. Our objective was to design a prototype water wheel that will be built upon in the future to generate electricity from a river. Here we have a simplified model of the system. From this, we were able to derive the mathematical model of the system and thus finding the Laplace of the models, determine the transfer functions, and step input equation. Lastly, a prototype was built and its capacity and value and valve resistance were found to predict its performance.
Upon completion of the project, the theoretical values were compared with the experimental results. By graphing the system, we were able to make the comparisons. These graphs compared well with the experimental results. Comparing the graphs with each other, test 1 is the least accurate and test 2 is the most accurate, with test 3 being in between. This is because our flow out is greater than our flow in, so at around 45 seconds we can expect the best performance at Q out. From an average of 45 to 80 seconds, it will have a more consistent flow rate. Anything above 80 seconds will have a drop in performance because of the level of the tank decreasing.
Final build model of our what?
Start over.
Okay. Alright, so this is the final build of our Waterwheel project. This hose here represent the Q in, which will be representation of the flow into from the river. The reservoir is used to hold the water at a certain pressure and level so that the wheel could get enough kinetic energy to spin. The valve here can control and vary the speed at which the wheel spins, which will be the Q out. To measure the Q input, since this lab was done at home and I do not have access to the proper scientific material, a simple 1 liter bottle was used and a stopwatch. The hose was added to the bottle and the time taken for it to fill to 1 liter. The same was done for the Q out of the system, but since it's so close to the water wheel, a simple hose was used. So the hose was added to the Q out and the same measurement was taken how long it takes to fill. The rotation of the wheel was calculated by using slow motion footage from our camera. We took the slow motion video in 240 frames per second, which is the equivalent of 1/8 the current speed. So we calculate how long it takes for one resolution in the slow motion, then multiply by 1/8 speed, divided by 1/8 speed, so we could get how fast it is in real life, which was the equivalent of 8 revolutions a second all the way down to 4 revolutions a second.